planned to make transparencies and use a projector, but I changed my mind and made handouts instead. Fortunately, with the room arrangement, it worked out best. Evening fellow Toastmasters. Tonight, I'll explain to you how the electric grid works. You'll hear about it occasionally, and this is actually by popular acclaim because one member asked me to discuss this. A little introduction. I worked for a number of years in the PG&E office. I was part of a Bechtel team that finished and fixed the design of the Diablo Canyon power plants, which are working very well now. And while working there, I learned a lot about how the electric utility operates. First, a little bit of history. Back in the 1890s, first electric plants were built. They were very small. They just provided power to small neighborhoods. I think Chicago itself had 20 different electric companies when they first started. Over the years, they got smarter, had better equipment, more efficient, and they merged, eventually ending up most cities having one large electric company. By the 1920s, they had merged. Then they started connecting each other with high voltage lines. This was the beginning of your interconnect system. Interconnections were high voltage. You can recognize a high voltage line because you have much taller towers than your local distribution lines. Generally, the higher the voltage, the more power they can handle. And as a casual observer, just observe the size of the insulator. So the longer the insulator, the higher the voltage. But the more noise you hear in your car radio when you go by. Finally, they all connected into three independent groups. Please look at your first handout. This shows the three partitions or sections of the existing national grid. The blue one is the eastern grid. It goes from New England to the Rocky Mountains, and it's also connected to the northern parts of Canada. Then you have the Texas grid is independent by itself. And you have the western grid, which is the Rocky Mountains back to the Pacific. It also goes to Canada. Each of those three grids, all the utilities are interconnected, but there's no connection between the three sections. No power can be sent. For those who are familiar with electricity, they're not in phase with one another. They're not synchronized. No way to connect them. Each of these grids is subdivided into various operating systems. Each operating system has what they call a dispatch control. And they balance all the power within their particular section. We'll use California as an example. We'll go to the next page. And this is California. The orange is the California, called ISO, the Independent Operating System. It's run by the state. Earlier, PG&E in Southern Cal Edison had their own systems. With the power crisis in the 90s, where those companies are bankrupted by some state regulation changes, the state took it over, and it's now operated by the state, independent service operator. As you see, there's a few islands in the center that are not controlled by the state. They run their own systems. In order to run a system, you have to match up your generation and your demand. So look at your next transparency. This is a graph, the ISO system for yesterday. As you see, the low power levels were about 4 in the morning, about 2,200 megawatts. The peak was late in the afternoon, 40,000 megawatts. So the demand almost doubles between low point and high point. Electricity cannot be stored. Generation must exactly match the demand. When you go turn on a light switch, demand goes up. Some machine in that operating network will sense the new demand, and some governor will open some throttle with very little bit to make a little more energy. And when you turn the switch off, it reverse happens. Everything has to be exactly balanced. Go to the next handout. This is a very interesting map. It shows all the power stations in California. The blue ones are the hydro, and if you notice, they cascade down the various mountain rivers. There's a series of small dams that the utilities built 100 years ago. And the larger plants are down in the valley. You study it later on, it gives all the numbers of what sizes they are, the totals and so on. A lot of information there, which I'm not going to go through now. The independent operator, dispatcher, controls all this power. It controls the hydro plants, the steam plants, the gas turbine plants, and the power that they purchase. California purchases a lot of power. Most of it comes from the Bonneville system, which is run by the federal government. These are the series of dams down the Columbia River and Snake River built back in the 30s. And there's two high voltage interties that connect with Oregon. That'll show on a later handout. They also buy a lot of power from Montana and Arizona. These are coal-fired plants because the various protests in California stopped utilities from building power plants, and they had to buy it from out of state. The dispatcher, as he handles his daily loads, has a lot of decisions to make. The first equipment he uses are what they call base load machines. These are a series of generators which are the most efficient ones, and they're fully loaded, kept fully loaded, even they match your night loads. And then the other ones are called load following. They are added during the days, and these are the ones that the sensors are set up so they will adjust themselves for load changes. There's a lot of constraints to this. One thing he has to do what they call spinning reserve. You have to have enough machines operating that are not loaded, not fully loaded, so that if your largest machine on the system fails, trips off, there's enough equipment operating that it won't cause an overload. Because if you get an overload, then you get a system like a problem like back in New York. Either your dispatchers are very smart and strip loads right away, or the whole system crashes. So they keep spinning reserve, and they keep adjusting, adding new machines during the day with the restraints that each type has. Steam plants, you have to be loaded slowly. Hydro plants have certain requirements because you can't open the gates real fast and give a tidal wave downstream. And so lots of laws and rules they have to follow on this for routine work. The plants that are used for daytime peaking have to be given a time when they be ready, so they'll have them warmed up and ready to load. Many of these plants have separate owners now. PG&E is forced to sell off all their fossil plants, so the different companies own these things, and they have contracts for how much they'll charge for how much per day and so on. Another restraint is the problem of renewable energy. They have to buy a lot of wind power energy, and they can't control that. Wind blows fast, makes a lot of power. Wind slows down and stops. The dispatcher has no control. He has to adjust the other plants for that. All he can do in emergency is trip them off. He cannot control the power level that's developed by your wind power. Also, he has no control over the various solar cell systems either. They're pretty steady. They go up in the afternoon and go off at night. But when a cloud goes by, they all dip their power generation. Cloudy days they do less. It adds to the difficulties of trying to balance the system. Now we have a smart grid. Most of you have heard that someplace. A lot of people advocating it. What is a smart grid? Well, this electric grid you've seen so far was not designed to distribute power nationwide. It was designed piece by piece, as the utilities grew up, to transfer power between adjacent utilities. Now we have a wind power movement. It's very powerful politically and financially. They want to sell wind power and build windmills. Much of it's in Texas. They want to sell power all over the country. So they are pushing for a new grid. They call it smart grid. Go to the next line, please. For the United States. The green lines are the really current, very high voltage lines. If you look at in California, you see those green ones, they go up to Bonneville. One goes on the ocean, Pacific Intertide, the one goes straight up is a record breaker. That's a 1,000,000 volt DC line, the only one I've got in this country. The yellow ones are the ones that they propose as a smart grid. These will interconnect the entire country, and if you notice those little black lines, they want to interconnect with the 3 grids. In order to do that, you require a very difficult combination of AC back to DC back to AC again. Very costly. It's proposed and advocated very loudly by interests that want it. Is it helpful? I'm not sure.
It's working as well.
Any time problems here?
No.
One concern is all these new things require new high voltage transmission lines. Show your last drawing. This is typical of a high voltage line. These are very costly and they're protested by most environmental groups. But if you're going to have the wind farms and super grid, you'll have that. In conclusion, you've seen how the grid works, you've seen the proposals for the super grid or smart grid. There has to be some changes to our current grid to update it to congested areas. I don't believe we need all the new things proposed. Thank you.